Good morning, everyone. Uh, how's audio and video? Everybody is copying me?
Okay, then let's start. Okay, this is the session 10 of the Global Hands-on Universe 2021. And we are in the last spin of this planet. And the first speaker of this session is the workshop of the creating astronomical images with the Hubble Space Telescope, presented by Melo. Okay, can we start? Can you start?
Sure, fine.
Okay, then please start.
So, good morning, everyone. Good night for some of you, like for me too. Here's 9:30 p.m. here in Brazil. Please feel free to interrupt and to make questions. You don't have to wait until the end. So, okay, so here's our workshop. Now we're going to create astronomical images with the Hubble Space Telescope. I'm a member of the Projeto Céu Profundo. It means Project Deep Sky. You can find us on our website, on Twitter, YouTube, Instagram, and here's my email. That's my name, Wandeclayt, Melo. You can call me Wand. And here we go. Here in GHOU, we have some previous workshops using real data, real telescope data, mostly from ground telescopes. And we had some workshops in the last year, some in 2021 also. So why do it again with the Hubble Space Telescope? So I think that these are really good reasons for us to choose the Hubble Space Telescope, just to mess around and to play with the data, or to bring it to the classroom, or to use it as a tool to communicate astronomy. Why? First, because it's the most popular telescope ever. Everyone who with some interest in astronomy in one moment or another in their life heard of the Hubble Space Telescope. So it's a good reference. It's everybody knows it. Also, it's been on orbit and it's been gathering data for 3 decades. So it has a really large database that's really comprehensible. It has planets, deep sky objects like nebulae, galaxies, clusters, you name it. There's everything in the database. Also, it's really easy to search and to access this data. So you can, anyone, no matter if you don't have any experience with astronomical data, we'll find it in in this facility, in this database provided by the Space Telescope Institute. There's something really important here. They provide calibrated data, so there is no noise. You don't have to make complicated reductions. So it's just ready to use. You download the data, you can combine it, you can mess around, you can play with it, and they're just ready to use. And also they have a great documentation. You can learn anything you want about the instruments, about the telescope itself. So we think it's a really good choice if you want to make your own astronomical images. So here's a view of the Hubble telescope. You can see that it's one telescope, but there's a lot of instruments there, a lot of cameras, and we can see that here. This is the field of view, and you can see the position of some of the cameras that we're going to use. This is the configuration that we have on the Hubble Space Telescope now. We had 4 17 missions, the last one in 2009. And these are the last cameras that were installed there, the WFC3, and the ACS was repaired. But these are the instruments that are working right now on the Space Telescope. So this is the link to the documentation. And right now in the chat, you can see the link to this presentation, so you can click on the links if you need. I sent you an email a couple hours ago with some links if you want to perform the activities. Right now you need the data. I will provide the link here again, but either way I've sent it on an email, right? So here you go. Let me see. We have people from Colombia, from Bombay, India, Peru. Hi everyone. So let's go. This is this one here that I'm showing is where we're going to search and look for the data here. I'll briefly present the interface and show how we can find this data, right? Okay. Right now, I will stop the sharing. Any questions so far? Okay, guess not. So here we go. I will share it again. And right. So hope everyone is looking at this window here. This is the interface to the Minkowski Archive for Space Telescopes. Another really good thing here is that this is the same interface that we're going to use with the James Webb Space Telescope. So if you learn it with the Hubble, in one year or so, you can use it to James Webb also. So it's one interface to a lot of telescopes, including James Webb. So my suggestion here is let's try something special, right? I mentioned here, let me see. This is an image of Mars. It was captured in 2003. It was during the opposition of Mars, when it was closest, the closest approach to Earth in the last 60,000 years. So perhaps it's a good opportunity to take images, to capture images, and to get the data from Mars. And hopefully Hubble did it. So let's try to find this particular data. So what we're going to do is here we can provide a target name. Let's try some NGC object like NGC 5139. This is Omega Centauri. It's a globular cluster. If I put it here, I say here resolve, and I click on search. It will take the object by its name. It will find its coordinates, and here it is, all the data that it finds around the area of this object. But this is not the one that we want. Let's try it again. We need Mars. So let's check it here. I will write Mars in the target name. If I click on search, there's a problem here. See, no data found. Why? Because there are no coordinates, no fixed coordinates for Mars. It's a planet. It's not fixed on the sky, so it cannot resolve it. You could try as don't resolve. Okay, now it's fine. So we don't need it to resolve. Resolve means looking at the name of the object and find the coordinates. We don't want this. but we also want to establish the time when this data was gathered. And we wanted in August 2003, that's during the opposition of Mars, during the perihelion, when it was close to to Earth. And we want to establish an interval here. So we're going to try here from 2003, from August first. And I need to establish an interval. So it starts in August 1st, and dot. And then again, 2003, Sep, from September, and 01. So now I'm going to look for data of Mars during this period. Most specifically, I will check this box here, WFPC2, because that's the camera that was installed on Hubble back then. That's the one that I'm going to use. And we're going to search. Okay, so what did you find here? What did I see here? A bunch of images made on August 26th and 2017. That's fine. That's during the opposition. So perhaps we will have some really close images of Mars. So I've sent you some images before in the link on the email. If you downloaded it, we can start playing with it right away. But let's take a look at the data that we have here. Let's look at this one. If I click the name of it, okay, it looks like some good data. I will check the other one here, a bit different. And let me try this other one. Okay, so it's really important to check the integrity of the data here, because sometimes the camera drifts or there's a lot of noise. So we have this preview here. But okay, where's the color? That's not what we were expecting, right? We want to make some. We want a color image of Mars, like we showed before. We have to compose it. To compose it, we're going to look for data collected on blue, red, and green filters, because Hubble cannot resolve colors. It's a grayscale camera. It's very sensitive, but it sees everything from ultraviolet to near infrared. And if you want some specific band, you have to place a filter on it. And we see it here, filters, gratings, it's this column here. And we're going to choose something that we know that is blue, something that we know that is green, something that we know that is red. And then we're going to combine these three images and make a color RGB image. From this data here are the wavelengths. And take a look here. Let me show it again. So this is the visible spectrum. It says electromagnetic spectrum, but it's just a tiny band here from the visual spectrum. So to the right there's there's infrared, and to the left there's ultraviolet. So this is what our eyes can see, from 400 nanometers to 700 nanometers. So we can roughly say that between 400 and 500 nanometers, that's blue. Between 500 and 600 nanometers, that's green. And above 600 and up, it's red. So we're going to look at the filters to find something between 400 and 500 and so on. And that's what we're going to do right now. So look here, this filter that says 4F400 F410. This here is in nanometer, but it's 408 nanometers. Okay, that's blue. That's a good one. We can use this one, the file that ends with 104M. The other one, it's 106M. If you see here, 502N, it's 502 nanometers. Okay, that's green, roughly green. It's a good one, 106. And let's find something in the red band. This one is nice, the 105M. Check here in this column, it's 631 nanometers. Okay, that's red. So we're going to pick these files, 105, 106, 104. Check these boxes, and next we click here, submit market data for retrieval. You don't have to do that because I sent you the data. You can download from Google Drive. But if you want to download it from the database, you submit. There's a new window here. Then you have to provide your email. Deliver the data to the archive staging area, that's it. You want calibrated data, and if you're using the WFC2 camera, it's the one that we use right now, you better check this option here, C0M. Otherwise, you have a lot of files, and this is the good one, this is the calibrated one. Once you do that, you click on Send Retrieval Request. It will generate a link. It will be sent to you by email, and you can access it using an FTP client. There will be some changes in this interface, and you will not need an FTP client anymore. But right now, you should use FileZilla or something like this. You don't have to do it right now because I've sent you the file. So let's work with this data right now. Any questions so far? Just let me check. I've sent the email to everyone who was registered, but you can use check this link here. Okay, I see that most of the people are accessing the presentation. The links are there for the data. These are the links for the data. Okay, you can download it for that. Okay, you don't need the email if you access the file here. It's this link that I'm showing here. So now I'm going to share with you the interface to this is the software that we're going to use, DS9. Let me go to here again. So this is the software that we're going to use. If you click here, you come here. DS9 is available to Linux, to Mac, Windows, and you can have the source code. If you have problems with the version that you're installing, you can take some legacy version and fool around. That there's here in the archive. There's the older versions. So sometimes, if the newer version doesn't work, try one of these legacy older versions, right? So, okay, so this is global hands-on universe. So let's go hands-on. Did any one of you install the DS9 so far? You have it?
You're going to share your screen, Wandeclayt?
Yeah, I'm going to do it right now. Here it is. Okay, I guess you can see it right now. You already see if you have the program installed, I will delete it here, start it from scratch. So this is the tool that we're going to use to compose our image of Mars. So the first thing that we have to do is we need to create a frame. That's where we're going to put our data, right? So you see there is 2 rows of buttons here in the program. There's this button here, frame. You're going to click here. It's already selected from here. So you click on frame and you click on RGB. Okay. It creates a new frame, and you can see in the bottom here that there are 3 lines, red, green, and blue. That means that we have a RGB frame, and we're going to stack 3 different files, and we're going to tint them with different colors. So there is no color in the files, but we're going to put color there. We're going to assign each one of them to red, green, or blue, and then we're going to combine them, okay? So here we go. I have this empty frame here. It says here single because it shows only one. I've clicked on RGB, so I made this one. And now we're going to open the files that we have downloaded, right? So when we create the RGB frame, we have this small window here. If you can't see it, you're going to, if it's on Windows, you have a menu up here. Otherwise, I have to click on this in the upper bar, frame, and then RGB, and then I'll get this small window here. So look at this. There are 2 columns. Red, it's clicked here, it's selected, and you have all these boxes here to view. So I'll keep them. I can see the 3 layers. There's none here, but they are selected. But I'm working on red. So if I open a file here, it's going to the red band. So I'll click on file in the bottom file here, not in the menu, in the bottom. And I'll click on open. And if you remember from the other window on the database search, we had these 3 files, and we checked that the red one was the one that ends with 105M. I'm going to open that file here. 105M, that's this one here. Open it. Okay, this is not what, oh, this is not the right one. Open it again. Okay, it's fine. So look, we have the file here. This is not what we expected, right? So we have to adjust a few things here. First, we should adjust the zoom. So click here in the button zoom, maybe zoom fit. Okay, now it's fine. Now I have the file on the entire window. That's good. I'll make it bigger. Zoom fit. Is it okay? Can you see it? Let's check here. Fine. Okay. So here we go. We need to adjust here the scale. So click here in the bottom scale. Instead of log, I'm going to use linear. Okay. Something happened here, but still not the mass that we used to see, right? So here's what we're going to do. In the upper menu, in the menu bar, click on scale, and then scale parameters, and we have this histogram here. Look, We have 0 here, and we have 40,000 here. And look, all the data is collapsed here, okay? And let's establish different values here. This value here corresponds to black, and this one corresponds to white. And we see that there is a very low value here, 50. So let's make it bigger. Let's put 3,000. I can write 3 E3. It's 3 with 3 zeros. Okay. Okay, a lot better, right? So it's a digital images. On a digital images, it means that the pixels are numbers, and I'm telling here that the number 0 means black, and the number 3,000 means white. So there's anything pure white here. Okay, if I make it smaller here, 1,000 perhaps, you see that I lose all the details. So I'll keep 3,000. Fine. This is the red layer. It's good. That's it's what I'm used to see to the telescope. So I'm happy. Now come to this small window here, and let's select the next layer. Let's select the green one. Click on green, and let's click on the bottom file, and now in open. And let's take the other file that we checked that the 106M is somewhere close to the green wavelength in the spectrum. So it's the 106M. It's this one. Okay. Same thing happened here. You see, it's too bright. So let's adjust it also. We come to the histogram. Instead of 50, let's put 3,000. Okay, a lot better. But we still have to. I'm going to unmark here, uncheck the red box to make it look better. Oops, wait a minute. The red one's fine. So let's look at the green one. Too bright, right? So let's put a higher number here, maybe 5,000. Oh, we forgot to adjust the scale. Click on scale. Okay, linear, it's fine. Strange. Oh, let's do it again. And what happened here is that I forgot to click on the green one again. So the red's fine once more. Now let's work only on the green one. So look, this is the green, this green light here. It's the value that I put here, 3,000. But look, there is still data above it. So 3,000 is not a good choice. Let's make it 5,000 and apply. That's better. And see, we should put the green light. It's behind the data here, the red one. So maybe here. Much better. Oh, the scale is log. Put it on linear. Much better now. Zero. Okay, but it looks a lot better. So what we have to adjust in the beginning, it's the scale here. So the pixels are numbers. We can apply functions to it. And the function that we should use here on planetary images, usually it's linear. Okay. Oh, the RGB small window. In the upper menu, you go to frame and then RGB. Okay. In the upper menu, not on the bottoms here. So check the green, I put the low limit on 0 and the high limit on 4000. Maybe we have to adjust something in, a bit later. But right now, if I check again the red layer, you see there are 2 layers here, but wow, there's something wrong. Okay, they're not matching. Anyway, let's open the next one. Let's select the blue layer, make it visible. Click on the bottom file, click on open, and the file 104M. I'm opening it. Here it is. Okay, so let's check the scale. Probably it's log. No good. No good for planets. Let's make it linear. A lot better. And let's adjust the scale here. Let's put it 1000. Let's see what happens. A lot better, maybe 2000, 3000. Let's see on it. Okay, this is the blue layer. But why are not the layers properly stacked? Because the planet moved. So Hubble is pointing to the planet, but Mars moved. And take a look at this. When I move my cursor here over the image, you can see the coordinates here. This WCS, it's the World Coordinate System. And I have the coordinates here, right? And what DS9 tried to do is to stack the images on the same coordinates, but Mars moved. So that's not what I wanted. I want to stack over the images, not over the coordinates. So select the RGB small window, and on the upper menu of this window, if you're on Linux or on Windows, there will be a menu here. I'm on Mac, the menu is on the upper side of the screen. Click on Align, and then on Image, and it will center it itself, okay? Now it looks really great here. We can see some really distinct features on the planet. We can also see this haze here. This is atmosphere, because we use for blue we use data collected really close to the ultraviolet, so you can see this haze from the atmosphere. And we can make adjust here to make it look better, make it look, it's really up to you. Let me see, what would I do? Perhaps I want a little more contrast here. Why not? So I will put, instead of 0 here, I'll put 5 on every one of them, the blue and the green. Apply. And red. Not much of a difference, but I can make it more, let me say 100 and see what happens. Okay, a lot more contrast. That's fine. Green, let's make the low 100. That's fine. And then blue, make it 2. I think it's with a bit more contrast, it looks better. But you can shift these lines around like this. It's okay. It's up to you. You can really play with it and see what fits better. It's really a question of what you think it's better. You can mess around. Okay, so if you like what you get here, you go to the upper menu, not to the bottom here. Go on File, and you go on this menu here, Save Image, and here you can choose the format that fits you better, maybe PNG. Okay, and then let's GHOU, and then you can export your image, right? It will export also this bar here with the values, if you zoom in, it will export exactly what you will see in this window. So maybe you should make it fit better, because that's exactly what is going to be exported, right? So any questions so far? Okay, we made a color image of Mars. And to make a color image of Mars, we took data from red light, green light, and blue light, and combined it on an RGB image. Sometimes we have to make different choices, right? When we create images of deep sky objects, of nebula, and we're going to make a new example here. Look, we're going to click here on frame and new. Okay, I've created a new frame, but look, this one is grayscale. It's not going to be you don't have to see color here. And I will open another image. So I wanted to check this here. Let me take another one. Take data from, okay, Uranus perhaps. Can't see anything here. Okay, it's black, so we have to adjust it. Let's change the scale. Perhaps log. Oh, fine. Change to log, and I can see something. What is this? Let's see. A really small value here. Okay, that's it. This is data collected on infrared. This is the planet Uranus, and we can see the rings here. Okay, you can go to that link to the search to search the database and check for the planet Uranus. Don't forget to uncheck the resolve button. And I got this data from the planet to try to look for the rings here, and you can see it here. And because this is data collected in the infrared, how can we know what kind of data do you have if you only find the file, if you didn't take it from the database? You can click here on file, and there's this button here, header. When I click it here, another small windows appear, click on OK, it's fine. And we have these properties. No, look, you cannot take more than 3 images here because DS9 has this limit of R, G, and B. But you can export them as feeds or any other format, and then you can combine them on GIMP, Photoshop, anywhere you want it. It's up to you. So when I open the header here, I can see a lot of information about this file. And I can see here that it was made in 2009. And there are information about the instruments here. The camera, it's a WFC3, but I want information about the filters. Should be somewhere around here. Instruments. And you see that it was made with, oh, here it is. This is the filter. 845 nanometers. That's way beyond the 700 nanometers limit of the red light. So this is infrared. That's why we can see the rings here. So you should check yourselves for Uranus data, and you can try to find filters above the 700 nanometers limit, right? And you can do things like that. You can change the visualization, just change the color. Okay, for Uranus, perhaps some cool colors like this should be nice. Okay, and if you adjust the histogram, you can recover some data here. It looks great. So there's time for a final example here. that illustrates what I want to show you here. Look, I'll click again on frame, RGB, and I provide some data on another folder. The link is also on this presentation to some planetary nebula. It's called NGC 5189. And it's a shell of gas expelled from the center stars, and there are wonderful data that there. Uses some very narrow band filters that select and they let pass through only some really tiny, really narrow portions of visible light. Particularly, they let the emissions from the double ionized oxygen, hydrogen alpha, sulfur, these gases, these atoms there in the gas, they emit some interesting filters that you can select with these filters. But then there's a problem because look, hydrogen alpha, it's a line on that emitted on 656 nanometers, 657, like this. So if you look at the presentation, you see, oh, okay, that's red. But the ionized sulfur line, it's 673 nanometers. That's also red. So how can I make some RGB image if I have two layers of red? You cannot. So we're going to put one of them on the green layer, okay? And we have the oxygen, the double ionized oxygen, it's fine also, it's 502 nanometers. But that should be something close to green. So I have red, red, and green. How can I make a RGB? So we're going to arrange it in a different way. Let's take a look here. So this is a new RGB frame. And I'm going to open as the red file. I'm going to use let me see, let's try the sulfur here, because it's the longer wavelength. It's the file, open. Let's take it here, 5189, that's one. And it's the one that finishes with 10. Where is it? Here. I open the data. I'll click on scale. Zoom fit. I can see it here. Now on scale. Let's going to change okay, now log, it's fine, but I have to take a look at this histogram here and see that the values are really small, 50, 100. So let's put the higher value here on 100 and see what happens. Oh, a lot of data here. Nice. Let's try 50. Why not? Even smaller, 30, it's fine. Okay, so we can see something here. Okay, so this is a good choice for ARP, yeah. Let's try another one. I'll keep the red selected and open another one on the same layer. I'll try the hydrogen alpha. It's the one that finishes with 20. Let's see if I have a better. Oh, a lot better. So I'll keep this one on the red. And let's change here for the green one. Let's open another one. Let's open the hydrogen alpha. It's the one that ends with 40 here. What is it? Okay, it's somewhere over here, but you see that there's something yellow here. Yellow, it's green plus red, but I want it to be brighter, so I'm going to use a smaller value here. But 50 perhaps. Oh, a lot better. The scale is already log, it's fine. So look, now I still have room to put another layer. That will be the blue layer. I will choose, I made a different choice here. I'll put on the green, I will put the 606. That's actually the a red one. That's 50. Here we go. So this is not a narrow band filter, it's a wide band filter. If you check it on the file, it says 606W, that's wide. So look, I took the hydrogen alpha filter, it's 657 nanometers. That's red, really red. Now I take the 606, that's also red, but that's a shorter wavelength. So instead of painted red, I painted green, and I combine them. It's already really looks nice, right? And now I'll put the blue one. I will choose it's 40. It's this one here. It's the oxygen line. Let's open it. Okay, I can barely see it here, so perhaps I should use a smaller value. That's it. Okay. See, you can shift the values here until you find something that you really like. But here's the important thing.
10 more minutes, Wandeclayt.
Fine, we just finished the activity. So look, sometimes you have to make some choices that it's purely statistical choices. We have a bunch of data here. So the only thing that we should try to respect is put the longer wavelength on the red layer and the shorter wavelength in the blue layer and the intermediate one in the green layer, and you should be fine. And then you can adjust the levels here. This data here are also available in the link provided in the presentation. You should try this. I will stop stop sharing. And let me check if there's any more questions. Okay. Apparently no questions so far, but the important thing here is all this data is freely and easily available. You can seek and download it on the provided link. And there's a lot of things that you can take to class, because if you see a new supernova, you can look for data from supernova. There's something about, okay, they publish on Nature that Jupiter is being heated by aurora. Okay, you can search for data on ultraviolet, perhaps, of Jupiter on the aurora and Jupiter. And it's really rich, it's really powerful, it's really available. You should try it. One last thing that I want to show you and that I want to ask you, it's to, if you make your own images, please share it with us, because this is what we've been doing during all these years with a lot of different audiences. See, this is a lot of images that we've been creating this workshop. The most of them created by the public, by the audience, and people without any previous experience with astronomical data, with any processing software. So you see, it's really powerful. You can do a lot of interesting things, powerful things with DS9 and the data made available by the Hubble Space Telescope. That's it. If there's no, okay, some comments. Okay, So stop sharing.
Let's thank
That's
Wandeclayt.
it. Thank you also. Thank you to the audience. My email is on the presentation. If there's any question that you have any time in the future, please feel free to contact me.
Toshihiro, did you want to introduce the next workshop? Oh, you're muted.
No, please take you. You take.
Okay. Okay, well, again, sorry I was late. I had trouble with the URL. My name's Carl. Some of you know me. Our next workshop will be in Spanish. And it's about something very interesting in Spanish. Hey, Eduardo, could you translate that for me?
I will try, Carl, but Spanish is not really my main. Maybe Wandeclayt can help us.
Sure.
Can a
Sure.
Spanish speaker help introduce this topic? I apologize.
Okay, on the chat, right?
The fanzine dioses y planetas. ¿Cómo se dice en inglés?
I'll need to read it. Sorry.
Fanzine gods and planets
Okay.
for children.
Fanzine? ¿Cómo se dice fanzine?
It's a zine. It's the same thing in English, but it's
If you're a curmudgeon, you don't know what that is. Sorry. Thank you. Anyway, so yeah, this sounds very interesting.
I think we still have a few minutes before the break, Carl.
Oh.
The break is on 1:35. So if anyone have questions.
Okay, boy, did I screw up? So questions for Wandeclayt, right?
right.
Wandeclayt, do you? It's okay if I ask one, guys. It's fascinating, really interesting talk. Do you? You know, are these images? Are they from on the Space Telescope site? Are those 16-bit FITS images? Do you know FTS?
Yeah. They are FITS images, 32 bits, I guess.
Oh, 32-bit FITS, floating point. Wow. Okay, well, you know,
I can check on the header.
No, and I liked how you're using DS9. I think Makali'i can do coads of images. Toshihiro can make color images, I think.
I'm not sure, but I think the Macari can.
Yeah, and Salsa J can, and again, I think JS9. We have a little simpler version of DS9. We use an HOU called JS9, which runs well on the web. So I think your activities would translate pretty well over to that. How you? I was amazed. How did you learn to use? It looked pretty simple by now. The HOU image search system. It was a mystery for 20 years. It was very hard. Somehow it got better. How'd you discover that?
It's because I'm on the interface between the amateur and the professional astronomy. I'm a physicist myself, and I know a lot of astronomers, and I go through a lot of. I use IRF here to reduce some data, and we use it here to present this workshop to undergrad students, and we think that it's really simple, but sometimes when some undergrad students go to pursue a major in astronomy, they see it for the first time. it can be haunting. So if we present it really early in the course, I think it's easier when they use IRAF or PIRAF and see DS9 for the first time. So we presented to high schools, and even for children, we had workshops with 80-year-old creating images with DS9, not with IRAF, just the DS9 like we did here.
Yeah. Now, Kate, could you make a little? We have it on our YouTube. Maybe somebody should make a little YouTube of you using that, and we should put it on our website of how to use that interface. I think that would, if we could see that easily, you doing that would be very, very nice. I mean, I think
actually, Carlton, for Portuguese speakers or maybe Spanish speakers, every Thursday night at 8 p.m. Brazilian time, we have workshops. We do a lot of different activities. We make mosaics. We do a lot of things with DS9 in real data, particularly HST data. We've been doing that since January. So if you go to our channel on YouTube, or Céu Profundo, it's our channel, you'll find a lot of these activities there. You are welcome. If you want me to record it in English, we can make it also.
Yeah, we find users around the world. I think that was very cute. I mean, I had many teachers, we'd write it, 10 years ago, write an email to HST, can we have an image, please, please? And 3 months later, an image comes back and we'd be so happy, one image. So
I totally volunteer to help anyone who wants to use the DS9. So you can have me as a volunteer and put me in touch with anyone who wants to learn it deeper.
You may not know what you're getting into, but we love it.
I know precisely what I'm into. And that's precisely what we the intention of our project here.
Yeah.
We love it.
And I'm thinking, like do an HST light curve of a supernova or the variable stars. What that's kind of mind blowing for me. I mean, we have a long time GHOU people like Fraser and Rosa,
yeah.
Who've taken, at great pain, download a few HST images and done good stuff. But this would be remarkable to scale it up and make it more useful. So yeah,
so sometimes we take some really long range data, something from I remember supernova in 2018, and we used image for 1 year period to see how it fades. And sometimes we take some supernova remnants and see how the gas is expanding. There's a lot of really fun things to do. Great.
Hey, can you put your email in the chat? And then we're going to send it out to 20,000 teachers around the world.
They're really welcome. I put it on the presentation that I've showed.
Yeah, something
before.
I could just copy.
Mm-hmm. But I put it in here too. That's the email of the project. And that's my YouTube channel.
Going in the chat?
It's on the chat.
Oh, okay, just a second.
This is the YouTube channel.
Oh, there we go. Got it.
We made a couple of weeks ago. Remember when Nature just published that article about the auroras hitting Jupiter. We went to the Hubble and we looked for ultraviolet data with aurora, and we made it live also. So we take things that get your attention and make something hands-on.
Very nice. Great.